We'll be solving the practice exam for exam 2. Um, and so let me begin by looking at the exam. So this exam, just like your exam 1, is also for 75 minutes. It has 6 problems and has 2 parts. Part 1 has 3 short questions for 15 marks, and then part 2 has 3 long problems for 35 marks. So this time the split is a little different. It's not 50-50. This is 30-70%. So there's a smaller emphasis on shorter problems. You know the sort of the style, so you will have to write some answers for part 1 as well. But let's begin and let's get to the practice exam. And this exam will be representative of the exam you will also get um, in your actual exam. All right. So let's start with problem 1. So it says, consider a steady flow of water flowing through a converging pipe, assuming constant density. Which of the following statement is correct? And then the options given are: external force on the pipe is 0, external force on the pipe is non-zero, is in positive x direction. External force on the pipe is non-zero and is in negative x direction. External force on the pipe is non-zero and is positive y, negative y, and any of the above. So clearly, this is a question of mass balance and momentum balance. And we have done these kinds of problems in class, and you have done many of them in homework as well. So let's begin. So we know from mass balance that A1, I mean, I'll just do it just so that in case you're kind of refreshing the material. So constant density control surfaces, V dot N dA is equal to 0. So V and N, and if I do like control volume like this, the N is pointing in this direction, N hat, so U1 and N hat are in the opposite direction. So you'll get minus A1 V1 plus A2 V2, because A1 U1 plus A2 U2, A1 U1 plus A2 U2 is equal to 0. Okay, so that's clear. And then from momentum balance, we know it's only the velocities are only in the x direction, so we'll just simply have it in the x direction as well. So we'll get, I just want to write it again just to, there is no rho because rho is constant. Control surfaces, V vector dA equal to F external, right? And so this is F external in the x direction only. So naturally the y direction components are all out because it's only in the x direction, flow is in the x direction, everything is in the x direction. So it's the x direction only option. So it could be either first A, B, or C, or F. So just to kind of make the point. But let's keep going from here. So V dot NV dA. So on the left hand side, it's negative. We have A1 U1 minus A1 U1. But the velocity is in the positive direction still. So it's A1 U1 square plus the right hand side is positive and the velocity is also positive. So plus A2 U2 square is equal to F external. We know A1 U1 plus A1 U1 is equal to A2 U2 from mass balance. So I can say A1 U1 minus U1 plus U2 is equal to F external. And then I know U2 is greater than U1 because it's a converging pipe. So this is greater than 0. The F external is non-zero, is in positive x direction. It's a pretty straightforward analysis. What I've done is I've substituted here A1 U1 is equal to A2 U2 to infer that I get A1 U1 minus U1 plus U2. And because U2 is greater than U1, because it's a converging pipe, then I get F external is positive and it's in the x direction. So this B is the correct answer. Okay. All right, so that was problem 1. And let's keep going. The second question is, which of the following velocity profiles are feasible? Select all that apply. A and B are constant. So clearly this is a problem from continuity equation, because we have discussed that not all velocity profiles satisfy continuity equation, which is the mass balance. So we want to make sure we satisfy the continuity equation. And to do that, we know and it's only in I hat and j hat, so we can only write in 2 dimensions. It's simply you can say del u by del x This del v by del y is equal to 0. So that's the so in the first case, both u and v are constants. So this one does satisfy. So this one does work because the derivatives of constants are 0. So both of them are 0. So this works. It's just a constant velocity. Then I have for this, I have u as then I'll get v naught by a minus v naught by b. And so this is not equal to 0. So this does not satisfy the continent equation. Then I have v naught by a. So this was 0 minus 0. Let me just to clarify. Substituting this here, 0 minus 0. Then I have v naught by a plus v naught by b. And this is also not equal to 0. Then I have the opposite, that v naught y by a. So that is now taking the derivative with respect to x for the y component. So that is 0 minus 0. So that does satisfy. This works. And then similarly, this also works. 0 plus 0 is equal to 0. So this works. So all three of them are actually able to satisfy. Okay. So we will in exam also, please make sure you're reading clearly. It says select all that applies. So, just make sure you're not just taking one and going away if you got a similar problem in your exam. Okay, just be careful of that. Other than that, this problem is pretty straightforward. It's just simple derivatives with respect to x and y. Okay? All right, let's keep going. Now, it says consider 3 pipes below of equal length such that R1 is equal to 2R2 is equal to R3 by 2. What is the relationship between different flow rates if pressure drop across the pipes is identical? This is if pressure drop across the pipes is identical. So basically, this is a problem that we have discussed in terms of resistances. And we had discussed this in class. So Q is equal to delta P by delta P pi R raised to the power of 4 by 8 mu L, right? So we had discussed this, that it goes R to the power of 4, right? And goes as by 8 mu L. So from that, clearly, we can just say for Q1 is proportional to R1 to the power of 4. Q2 is proportional to R to the power of 4. Q3 is proportional to because R3 to the power of 4. Because rest of the properties are the same. Pressure drop is the same, viscosity is the same, and the length is the same. Clearly, it's equal lengths, right? As written in the problem. So Q1 is basically R to the 4th. So Q1 by Q2 is equal to R1 by R2 to the 4th. And R1 by R2 is equal to 2. So this becomes 16. Okay. So Q1 is equal to 16 Q2. Okay. Similarly, we know Q1 by Q3 to R1 by R3 to the power of 4. I believe this is half because actually my apologies, did I make a mistake here? Actually R1 by R2 is 2. Okay, that's fine. So, and then R1 by R3 is half. So that's okay also. It's 1 by 2 to the power of 4. It's all right. So this is 1 by 16. So Q1 is equal to Q3 by 16. Okay. Which kind of makes sense. So it's saying that the second pipe will have the lowest flow rate because the thinnest one, and it goes R to the power of 4. And the thickest pipe, R3, will have the largest flow rate. So basically, we get D. This is what the D is suggesting, right? This is the answer. So this is very clear from the overall the relationships we had discussed in the class about how resistances go as R to the 4th. So basically that's the main point here. All right. Okay, so let's keep going. So the short problems are over. So now let's keep going to the longer problems. So now the fourth problem is consider a system of connected pipes below such that water inlets through pipe 1, cross-section area A1, and inlets through this, and then exits through pipes 2 and 3. So it's coming from 1 and going through 2 and 3, the two pipes towards the right, which is seen in the figure. Then the density of the water can be assumed to be 1000 kg per meter cube. P1 is the gauge pressure at the inlet. The gauge pressure at the outlets are given to be 0. So it's only pressure 1 that we need to worry about. P2 and P3 are 0. And we have to find external force F with P1. We haven't given pressure, so whatever is remaining is the remaining external force. And express your answers in terms of velocities, cross-section area, theta1, theta2, and b1. Okay, so this is a very classic problem from mass and momentum balance. We have done many of them in class, and you have also done this in your homeworks. So let's start with the mass balance. And I believe these things will become hopefully second nature to you now. Control surfaces is equal to 0. So from here we know that the normal to the first one is opposite, and with the this one is with the velocity. So this simply becomes a1 u1 minus a1 u1 plus a2 u2 is equal to a3 u3. So this is very clear. This is the mass balance, and also makes sense from the continuity equation usual that inlet. Sorry, a1 u1 plus a3 u3 is equal to 0, and also makes sense from the usual equations that we have seen before. Okay. Now, for momentum balance, we have to be careful because we wanted to make sure we do both in terms of x and y. So momentum balance is v dot n v vector dA control surface is equal to 0, not equal to 0, equal to f external total summation of x external total, including the pressure force. So whatever remaining would be the f vector. So let's start with the x direction first. The x direction. So the left hand side is again minus a1, and there is also a rho. Let's not forget the rho here, because I'm writing this equation undimensionally. By the way, I might have missed a rho in the part 1 as well here. There is a rho. Apologies for missing that rho. Okay. Yeah, so let's keep going. I sometimes forget the rho because of constant density. All right, so let's keep going. So minus rho u1 a1 u1 square a1. Okay, and now then in the right hand side I have u2 square a2 and u3 square a3, but I have to take the components now, right? So plus rho u2 square a2 cos theta 1 plus rho u3 square a3 cos theta 2 is equal to P1A1, because P1A1 is acting in the positive direction, P1A1 plus F external x. So whatever is remaining, F of x, basically, F of x. The F vector that has been asked, the x component of that is this. Okay. So essentially, I have F of x as P1A1 plus rho u1 square a1 minus rho u2 square a2 cos theta 1 minus rho u3 square a3 cos theta 2. All right. Similarly, for y, we can do that. In the y direction, we don't have any component from the inlet because it's only in x. So we will have we'll take the components from the outlets, sine theta and minus sine theta 2, because this one goes in this direction and this one, the upper one, goes in the top direction. So basically we get rho u2 square a2 sine theta 1 minus rho u3 square a3 sine theta 2 is equal to f of y. Okay. And so I have f of x and f of y. So basically my f vector is simply fx I hat plus fy j hat. I don't have to expand more. So this is what I have. So I have these three equations that I will box now that are my main results. All right. Okay. So let's keep going. Now the question is, you are given that theta 1 is equal to theta 2 is equal to pi by 3, and f is only in the x direction. Okay. we are given that U1 is equal to this, A2 is equal to this, A3 is equal to this, P1 is equal to 10 kilopascals. What is the value of F vector? Okay. So basically, we have been given that F is only in the x direction, which means that F of y is equal to 0. All right. So it's, and we have been given sine theta 1 and sine theta 2 as well. So it's saying rho U2 square A2 sine theta 1 minus rho U3 square A3 sine theta 2 is equal to 0. Okay. And so this gives me the, essentially, I know the value of U1. Okay. And I know the value of A1, A2, A3. And then I also know the value of P1. What I don't know is the value of U2 and U3. So I have this equation that has been given to me in terms of U2 and U3. And then I also have another equation, which is A1 U1 is equal to A2 U2 plus A3 U3. So A1 U1 is equal to A2 U2 plus A3 U3. So technically, I can solve for both U2 and U3 and then plug this back in here to get the equation. Okay, so let's do that now to get the final values. So from here, I can say U3 is equal to U2 into A2 sine theta 1 by A3 sine theta 2 square root. Okay, and so this is the part for U3 is equal to U2, and then I get U2 is equal to A1 U1 plus A2. So I'll substitute this back here, plus A3 times A2 sine theta 1 plus A3 sine theta 2. Right? So let me make sure I'm not making any mistake here. I believe this should be okay. So let's do this calculation. I'll just quickly pull up to put these values in. All right, give me 1 second. So let me put the values. So A1 is, give me 1 second. A1 is 0.1 meter, 0.1 meter square. U1 is 10 meters per second. So, and then we have A2 as 0.063. A2 as 0.063. And then I have A3 as 0.037 and 0.037. All right. And then sine of pi by 6. So let's calculate U2 is equal to U1, U into A1, U1 into A1 by A2 plus A3 into A2 sine theta 1. So square root as well. Square root A2 sine theta 1. A2 is 0.063 into sine theta 1. Sine theta of pi by 6 is half, so 0.5 by 0.037, A3, 0.037 into square root of 3 by 2, which is the sine x, which is sine 60. And so this U2 comes out to be 10, almost 10. So U2 comes out to be basically 10 as well. So this comes out to be 10 meters per second. Okay, and then let's also do now U3 calculation. And then U3 is A2 sine theta 1 into that square root times 10. So 10 into, that is also essentially 10. So this is also 10 approximately. Okay, so this is essentially all the values are the same. That's what that's sort of probably the way the problem was set up to kind of make sure it all comes out to be 10 meters per second. And now we can plug this back into the formula. So we have fx is equal to e1 a1. So 10 to the power of 4 into a1, which is 10 to the power of -1, plus rho u1 square a1. So 1000 times u1 square is 10 to the power square. A1 is 0.1 minus rho u2 square a2 cos theta. So again, it's 10 to the power of 3 into 10 to the power of 2 into a2 cos theta, so which is 0.063 into cos theta of cos theta 1, I believe, which is 5/6, so the square root of 3/2, and then minus 2u squared, so same 10 to the 3, and because the value is 10 everywhere, and then cos theta 2, which is half. So first, let me get the area as well. 0.037 into cos of 5/6 into half. Okay, so this is the value in newtons. So let's see what the value comes out to be in terms of this value. So it's 10 to the 3, because kilopascal times area, 10 to the 3 plus 10 to the 4, and then minus 10 to the 5 into 0.063 into square root of 3/2 minus 10 to the 5, 0.037 into 0.5. So that comes out to be 3694 newtons. Okay, 694 newtons. All right. So that's the value of fx. And by the way, this is all my f vector because fy is 0. So f vector is 3694 since fy is 0. Okay. So this was essentially the problem. This is sort of like the usual mass and momentum balance in pipe networks. So hopefully this makes sense. And yeah, let's keep going. So the next is show that the velocity profile above satisfies the continuity equation. So it's clearly a question on velocity profiles and continuity equation. So my v theta is equal to a by r plus br 1 by r del by del r of r vr. By the way, this has been given to you on the last page. You don't have to memorize this, but I just remember this, so I can do this. Now VR is 0, so simply this goes away. V theta is not a function of theta, so this also goes away. So 0 is equal to 0. So this is pretty easy, and you can get this. Okay. So the second question now says express the velocity in Cartesian coordinates. That is v vector is equal to ui hat by vj hat. So v vector essentially is a by r plus br is br into e theta hat. Okay, so v vector is equal to e theta hat. And so first I'll convert e theta hat into sine theta and cos theta, and then I'll go from there. So e theta hat is minus sine theta I hat plus cos theta j hat, right? So let's go from there. So this becomes essentially a minus sine theta by r minus br sine theta. Br sine theta I hat plus a cos theta by r plus br cos theta j hat. Okay. And this is not very difficult, but we know that sine theta is essentially y by r, so it will become y by r square. And I can convert this into simply, because I want to express this in terms of u and v in terms of a, b, x, and y. This basically becomes minus ay x square plus y square minus by, right? So this is y, and then sine theta is y by r, so it's r square is x square plus y square. So I had plus a cos theta by r. So same idea. So ax by r square plus bx j hat. Okay. So this is equal to u. This is equal to b. All right. So this, I guess that's it. This is the what part which you have to do. So this is done. Now find the stream function using the relationship u is equal to del psi by del y and v is equal to minus del psi by del x, and show that psi is equal to this value. Okay. So this is what we've been asked to do. So I have u is equal to minus ay x square plus y square minus by. So let's go here. So del psi by del y is equal to minus ay by x square plus y square minus by. Okay. And here, so this essentially when I integrate this respect to psi, the derivative of psi, I mean, in this hopefully you can see the derivative of this is y by 2. Sorry, 2y. So I have to multiply and divide by 2. So minus a by 2 log of x square plus by y square minus by square by 2 minus by square by 2 plus c of x, c1 of x. Similarly, I also have del minus del psi by del x equal to ax by x square plus y square plus b of x, I believe that was yes. And this is x square plus y square to keep it consistent with x and y. So similarly, if I do this, I'll get psi is minus a by 2 log of x square plus y square minus bx square by 2 plus c2 of y. All right. And basically this part is common, but this part is not, but this is only a function of y and this is only a function of x. And I'm allowed to add a constant, so I can simply just add the two sides in a way like this part, these functions, add them and make a common one, which is minus a by 2 log of x square plus y square minus b of x square plus y square by 2. This way I kind of make it common. There's some constant which is neither a function of x and y. So this is a way, this is something we have not done in class, but hopefully you can see this as an example. And we know that this is equal to minus a by 2 log of r minus br square by 2 plus c. So this is log of r square, or we can say minus a log of r because it's a square minus br square by 2 plus c. Okay. So this is actually a and b are reversed here. So a and b are reversed, but that was just a typo. We'll fix this on the canvas side. Okay, so this is essentially what problem 5 is. And yeah, this is it. So just to clarify, we started with the usual continuity equations, converted e theta hat into sine I hat and j hat, collected the terms called u and v, and then did some integrations to get to the final answer, which matches with the given answer in the solutions. Okay. All right, so now let's keep moving forward. We have been given consider a steady unit direction combined pressure and shear for driven between two parallel plates, as you see below. And the top plate moves the velocity u naught in the positive x direction. So it's basically both pressure driven and shear driven flow. And we have been asked to find the value. We have been given that the velocity profile in the x direction is like this. It's steady unidirectional, so we can simply use the parts we have been given. There's no gravity given, so we can just simply ignore gravity. And so we can say small v is equal to 0. Pressure is not necessarily constant, but we can say gravity vector is also equal to 0. So we can say del v by del x plus del v by del y is equal to 0. This is equal to 0, which implies u is only a function of y. Okay. And from the x momentum equation, we can do this is something we've done many times before, but let's keep doing del E by del t, u del E by del x plus v del E by del y is equal to minus del p by del x mu del square u by del x square and del y square. Okay. This is steady, del E by del x is 0, v is 0, del E by del x is 0. So we get this. From the y momentum equation, I don't want, you can show it, it's pretty obvious. Everything is 0 except del p by del y. So this implies that is p is a function of x. So this is very standard. You will almost always get this in the Cartesian coordinates for any directional flow. Basically, our equation becomes dp by dx is equal to mu d square u by dy square. Okay. And because left hand is only a function of x and right hand side is only a function of y, I can essentially call this to be delta p by L. Mu d square u by dy square. Okay. All right. So now from the boundary conditions, this is very important. We know that u of 0 is equal to 0, so that the bottom plate is not moving. 0 and u of capital H is equal to u naught. Okay. U of capital H is equal to u naught. That's what's moving. And so when I integrate this velocity profile, this is something I am very habitual of, and don't worry if you're not. That's don't worry about it. You will slowly, be able to get to this answer. I will just quickly write this just because I've seen this kind of many times. All right, so this is the answer we should expect. That it is the delta p by L minus delta p by L actually minus delta p by L x square by 2 mu into 1 minus, actually not 1 minus y by x square, but y by h minus y square by x square, because this is from 0 to h plus u naught y by h, and this is equal to the velocity profile. So how do I know this is the correct velocity profile? Is I can check the boundary conditions. If I put y equal to 0, everything goes away, velocity gets to 0. And then if I put y equal to capital H, then also I get u naught back, which is my boundary condition. And don't worry, you can integrate this and to show. I'm just not showing the details in the interest of time. And so I get this, and I've been given that this is sort of 6u1. So my u1 essentially is a 6u1. So u1 becomes minus delta p by L x squared by 12. Okay. Because 6u1 is that. So this is my u1. So now the question is, what is the average velocity? Express your answer in terms of u1 and u2. So the average velocity u bar or u average is equal to, we go from 0 to h, I believe. 0 to h, there is a width, but that gets cancelled out. U of dy. So width gets cancelled out. So this is u1 into 1 minus y by h minus y by h whole square. Whole square dy 0 to h plus u2 y by h u naught, rather this is actually should be u naught, not u2, plus u naught y by h dy 0 to h by h. So what we really get out here is u1 into, if you integrate this, it will become y square by 2h and y cube by, so this will become 1 by 2 minus 1 by 3 plus u naught into half. So we get u1 by 6, u1 by 6 plus so actually there was a 6 u1 here, so apologies. So there is a 6 u1 here, that's why I was a bit confused. So you get a 6 u1 and 6u1. So you essentially get back u1 plus u0 by 2. This is the average velocity. Yeah, 6u1 into 1 by 2 minus 1 by 3 plus u0 by 2. So u1 plus u0 by 2. And what is the value of shear for this per unit area on the top plate? Specified answers in terms of mu, u1, u0 again. Not an h. Under what conditions does the shear force per unit area vanishes? So we have the velocity again, u of y is equal to 6u1 into y by h whole square plus u0 y by h. So tau, the top plate, the top plate has a negative vector pointing downwards, so you get minus del by del y is equal to y equal to h. So we'll take the derivative. Now 6u1 into y by h is 1 by h minus 2y by h equal to capital H plus u0 by h. And the right hand side is this is just constant, doesn't depend on y. So we get minus, and so this is actually plus plus 6. So mu into 6u1 by h plus u0 by h, or mu by h into 6u1 plus u0. I believe that is correct. Sorry, minus u0. 6u1 is minus u0. 6u1 minus u0. Let me just make sure this is it sounds correct. I think this should be all right. And then what we have been asked is when will this go to 0? So tau top will go to 0, and 6u1 is equal to u0. Okay. So this is the last problem, and hopefully this kind of helped you. We'll correct some of these typos in the practice exam and then post the corrected version. But let's quickly recap what the kind of problems we did in this practice video. So first one was the converging duct. We did a momentum balance and the mass balance. It was easy to show that the FX came out to positive. The second one, we simply put the values on the continuity equation and got the options. Then we used the resistance formula that goes as r to the fourth, which gave us this answer. We did the mass and momentum balance in both x and y momentum balance, and got the values of fx and fy. And then we showed how the values for u3 and u2 are the same as 10 meters per second as u1. And then we also calculate the value of x, which came out to be 2,694 newtons in this mass and momentum balance problem. Then we had a continuity equation, where we applied the cylindrical coordinate equation, and then we calculated u and v. And then we also calculated the stream function and showed it was equal to the one that was given in the problem. We did the velocity profile calculations and came up with the velocity profile. We found the value of u1 and showed how the average velocity is just u1 plus u0 by 2. And that for the shear stress to go away, we need 6u1 is equal to u0. Okay. So I think that's it. And hopefully this video was helpful. We'll also post the solutions, and we look forward to seeing you in the exam.